That. Okay, so now I can talk. Yes, thank you very much for the introduction. Maybe, thank you, Pyonghwan and Yungjun for the invitation. Actually, at a very short notice. But before Pyonghwan asked me, he know me, going to give a lecture at the Chongqing school. And he said, well, if you have time, maybe you can come here for a few days to give a seminar. I said, no, now the COVID is very strict. I have to follow, make plans long before that. But then now, it's again due to the COVID, then I have to delay 2 days. So I say, well, okay, so now I can make that talk. Thank you. Thank you for the arrangement.
Yeah, the same COVID.
Yeah, the same COVID can do different ways. So the model maybe also can go all the way. So it depends on what are the outcome of the final result. Yes. Yeah. So today I'll talk about something about the g-2 for Muon. From some theory, basically you have some z prime. Then of course this particular model has some Muon gauge symmetry, Lipton Muon number minus Lµ-Ltau number. Well, this is a very simple model, which actually is the simplest model. You can add a gauge group on top of SU3 without enlarging the particle contents. Okay. So that's why some people like to work with this model. This model doesn't want to. Okay, so I'll first talk about this model a little bit for the 2, and then I'll say how the g-2 will give you some information about this z prime mass in the model. It turns out in the usual model, it's going to be very small mass, less than 300 MeV or so, in order to satisfy and known some other constraints if you want to explain g-2 for Muon. But then, because this become a sort of a folklore, so well, okay, so if you talk about the z prime, and then you want to solve for g-2, then people say, well, okay, if you consider constraints in particular, Trident experiment or experiment later, then it must be less than a few hundred MeV. But then here, find a way to invade that sort of limit. In fact, in this type of model, z prime can be small, and also can be large. It depends on what particularly details you have for the model. Okay, so now I'll draw some conclusion. Well, because of this, then the modification, you have some sort of new predictions which can be searched for in future collider experiments. If it is large, it's small also. Okay, so g-2 anomaly in a standard model. So why it is an anomaly? So you have to define your standard model first. But then we know the standard model well. Now the gauge group is SU3 cross SU2 cross U1 color W and B. The combination for this is electroweak symmetry, right? And then once you define your gauge group, then you have to also define what other particles are there in the model. So now we have 3 generations of quarks and 3 generations of leptons. And of course, because this thing, the gauge particles gamma, gluon, Z, and W. And of course, you need the Higgs to give the masses to all the models in the standard model, the particles in the standard model. Okay. But then maybe before going into the details, you may be wondering, why we don't just talk about the 3 generations, or what about the 4, 5, or something other numbers? Okay, so there are good reasons that there must be only 3 generations if you take this particle content, and then you say Higgs gauge bosons, and then you not allow the variation of generation numbers. Okay, so one of the factors is the discovery of Higgs at LHC. The main contribution is from glue fusion to Higgs. So this glue in the pp proton, and then this is the dominant contribution. So if you calculate this, you find that it's the one in the loop who has a mass which is bigger than W and Z, that sort of thing. So if it was a 3 generation, you will have just one heavy quark in that definition. Okay, so then if you normalize to the number of the normalizer to be 1, but then this is 1 generation of a heavy quark, then the cross section is proportional to the number of heavy generation. So this is a 1 for a 3 generation, you just have 1. But then if you have a 4th generation, we don't see the heavy 4th generation. It must be heavy. Okay, so then they become 1 becomes 3 because you have 4th generation. You have up-like and down-like 4th generation, which must be also heavy. So it becomes 3. So then it basically becomes 1 squared against 3 squared, which is 9. Okay, then you go back to compare with the data. They say, okay, you guys do the calculation, maybe you have some error bars. Okay, it's another 1, it's a 1.2, maybe 1.3. But then if you want to make it to 9, that is sounds very unreasonable. If you have a little bit of confidence in your theory, then you should not say, well, I shouldn't go to 9. Otherwise, I will be in contradiction with experiment data. So from this fact, people believe for quarks, there are only 3 generations, not 4, not 5, not bigger numbers. Okay, but then of course this is in the standard model. Standard model here means you only have 1 Higgs doublet. You only allow the generation number to vary. But then what about leptons? Leptons, of course, you haven't known all this for a long time, and Z can decay into 2 neutrinos. In the standard model, that's a fixed sort of interaction strength. So you can compare with data, and then for this decay, if mass is small, much smaller than this, then you can calculate it with good precision, and then data constraint, this number must be 3. Actually, that is exactly 3 experiment is 3 point something or 2.9 something. So in any practical sense, it's 3. And there are also cosmological bound nuclear synthesis, the primordial nuclear synthesis. And the light neutrinos will affect the nuclear synthesis time, the Haber constant, such that they will change the interaction rate. So in order to it work well, it should be also 3 point something. Okay, you have heard about the darker darker radiation, maybe 3.4, and then 0.4 maybe from something else. But then, as far as the neutrino number is concerned, if it's less than 4, then it's 3. Right? So there may be something else, but then this here I exclude something else first. So this also says light neutrinos are just 3. And then you say, well, maybe the 4th generation of neutrinos is heavy such that this cannot decay, and it's heavy such that this will not affect the Haber constant, the primordial nuclear synthesis constraint. And then you come to some other argument will help you determine the lepton number. Also must be 3 if you fix this to be 3. That's the anomaly cancellation of the gauge anomaly. So gauge anomaly basically say, well, you have some fermion running inside. You have 3 gauge bosons. These gauge bosons can be the standard, any one of the standard model gauge boson. Now, in the standard model, the fermions are organized into left-handed and right-handed. So if you let the left-handed particle running inside and right-handed particle running inside, they will contribute differently with a different sign. Then you say, okay, now it turns out in the standard model, each generation, the quarks produce some anomaly, left and right, and the leptons also create some anomaly, left and right, guys. But then the sum over is equal to 0. Okay, so now considering this, you have 3 generations. If the gauge structure is already fixed, so in order to have the complete cancellation of gauge bosons and anomalies, and then you only can have 3 generations of leptons too. Okay, so then once you have this, now in the standard model, what we are talking about is a model with 3 generations. This model, the minimum standard model, works very well with data, except in the neutrino sector. Neutrino mass requires some additional information about neutrino itself. But then, if you introduce a neutrino to be right-handed neutrino, which is completely singlet, then it will not affect my argument here, because Hegel normally doesn't participate at all. But then if you say, well, this particle is from some gauge group, then it will affect. Okay, but then for our practical purposes, you say, well, we have 3 dimensions, everything is working well, it's a neutrino, and some other anomalies exist right now from experimental data. One of them is the g-2 anomaly for Muon, which now is 4.2 sigma. This is a sigma from standard model prediction. So that is what people from last year was worrying about. But in fact, 20 years ago, from Brookhaven National Laboratory, they measured to high precision. At that time, was 3.3 sigma. But last year, when Fermilab result come out, they confirm the data from Brookhaven, and then they say, well, this is even more serious. 3.3 sigma or 2.7 sigma become 4.2 sigma. So then people will say, well, maybe we need to really worry about it. So last year, when the data come out, immediately the first day I think is 40 of some paper, next day 60 papers, and then people writing in continuously for some week. And now still have some occasional papers, but I think the main ideas have been expressed. We have to wait for another new generation of data to come and then continue to pin down the situation. But besides that, I will continue say, well, okay, so if you want to expand this data, what we need to do. I think many of you already know. So if you have some spin interaction of magnetic field, the Hamiltonian looks like this. Okay, and so basically you measure the precision of the spin in magnetic field. And then for Dirac equation, if you think electron, for example, then you can naturally work out the interaction. This mu is given by this formula. Mu is equal to electric charge, or electric charge, and this G factor, and the spin divided by 2 times of the mass. Okay, so for g-2, for a Dirac particle at the tree level, then this G is exactly equal to 2. Basically, now, if you do quantum field theory, then you would say, okay, so I have this Feynman diagram. This tree level Feynman diagram will give me some contribution of g-2. Okay, But then, of course, when quantum field comes, then you have a higher order corrections. For example, you have a one loop correction. This is just QED, electron and photon. This was first calculated by Schwinger long time ago, 1940s. And then you find that this will have a finite correction to this 2. But then if you define the g minus 2 divided by 2, you find that this correction to this factor 2 is alpha divided by 2 pi. Okay, it is small, but then it is now experiment data is way better than this one loop precision. So that has been measured very well. In fact, then you have a QED calculation, 5 loop level, or we calculated, and then at high loop, then this photon here, in between, you can also have hydrons to come in, and then you have to evaluate this at the same order of alpha expansion or something equivalent. Okay, so it's very well measured. Okay, so then now you say, well, you also have a very precise measurement of experimental data, and then you also have a so-called very precise theory. Then you will find now across the Bremen data and the new Fermi data, this is before the calculation. Before the Fermi lab data, then this is standard model and the experiment data have just the Bremen alone is about 2.7. But then Fermi lab, let's say they have a 3.3 difference. Then if you combine them, the significance increased to 4.2. So the difference is 251 times 10 to the minus 11, the error bar is 59. Okay, so if we take the face value here, then it's a 4.2 sigma, and then a lot of people is excited. Oh, okay, so my theory probably is going to be confirmed. And then a lot of persons come and say, oh, I have another theory. There are too many theories now can produce this 4.2 sigma. Well, this is from one side that you try to explain. But then some people they say, well, maybe your standard model calculation is not so precise. In fact, just after the Fermi lab data come out, is this lattice calculation here. Their central value compared to this central value is not 4.2 sigma, just 1 point some sigma. So then this raises the question: do we really have good understanding of experimental data? And another way of trying to ask is, do we really have a good calculation of a theoretical prediction for g-2 for Muon? Right. So you can look for both sides. So experiment then just continue carry out more and more precise measurement and determine more precisely. So Fermi lab has continuing and collecting data. Maybe next year they will update the new results. And then from theoretical side, you say, well, okay, now the previous calculation with all these model calculations plus some lattice calculation. This is the new lattice calculation, but still there are several other groups are doing similar things. So maybe another 1 or 2 years, this number will have more convergence, whether we really understand the theoretical calculation of g-2 Muon. Okay, so this is the situation now. But then, because, yeah, yes.
So can we understand why there is such a large deviation between two lattice calculations?
Yeah, for example, here and here. Well, they use different methods. Okay, one is using the dispersion relation. I think for basically is see these just the photons and the electrons. This is well under control. But then when you like this, you have hydrons inside. How do you take all these hydrons in the loop or in the blood, then that's a problem. So
That's why people use the lattice calculation.
yeah, they trust that maybe lattice can do the best. But then before that is then you have some other theoretical models like dispersion relation. You know the real imaginary part. You know the real part, and then you can extrapolate your data and then get some number. So that's why each method have some differences. Basically, due to the theoretical method we are using, and each method has some not so well understood errors. Yeah, but then people believe this lattice calculation probably is the ultimate sort of tool to determine this. Okay, so now what is the? But then, as I said, many people say, well, okay, we leave to experiment and leave to some other people to determine the differences. But if I take the face value here, what can I do from beyond the standard model point of view? Okay, so beyond the standard model here, I will talk about this particular model. Why this is good? And for this particular thing, yeah, you see, this mu particle has interaction with the muon. So this concerns the muon. It doesn't have an electron, so it will not affect the electron. However, then the data is much worse. So then this might have a chance at least to solve the problem and then leave the other sort of effect intact. So maybe have a good chance to survive. Okay. So what is this model? Well, this model basically you say, okay, so in the standard model, you have 3 generations for leptons, E, mu, tau. And the E, mu, tau, you know, each one has some lepton number, electron lepton number, muon number, and the tau number. And then the theory actually has a global symmetry if there is no mixing for these quantum numbers. But then you say, well, can we gauge these quantum numbers? Okay, yeah, you can. But then you can, then you have to say, well, whether, because these are leptons, the left-handed doublet, right-handed singlet of the SU2, and the different hypercharges. Then you say, I needed to do such a way that they will not upset the gauge anomaly cancellation. Okay, so the simplest way, without introducing any new quantum fermion particles, that is the Li minus Lj. This can be any one or any two of it. Why? Because this one is plus, one is minus. They always just one produce something, another generation of leptons to cancel it out. So this happened because of this hypercharge. In this anomaly, you can come in have one hypercharge, and then there's SU2 or the SU2 is no SU3 because they don't have a strong interaction, or 3 hypercharges. So then you have y to the third power, y to the 1 power. If you have one is positive, another is negative, they always just cancel each other. So that's why this is so easy to do. But then in a long time ago, 1991, before that, people don't realize it. But then some realize it, but then don't take it. Well, maybe it's something you can do beyond the standard model. So that's why I was in Melbourne. So your supervisor and the reworkers and several others. So we say, well, okay, let's take it seriously, see what happens. Then we build a model to do it. Okay, so now you take it, well, this is the way of generating new interactions. Then you will find out, okay, so let's say mu minus tau. That is the mu interaction with this. I normalize it to be 1 in this gauge coupling. Then the tau will be minus. Then the corresponding neutrinos will be also like this. Okay? So now you notice the second generation I have a muon interaction and also neutrino interaction. Okay. As I said, for tau, you have less accuracy on data. So when you do this very precise calculation or measurement, this one gives the most stringent constraint. Okay, so this will be our emphasis in this model. But then before the Brookhaven data come out, people do various of calculations. So we searched for whatever lab data at that time can do it. But then g-2 has not come to a sort of central role. And then when the Brookhaven data, yeah.
Can I ask one thing? Are left and the right-handed fermions charged under this Z prime? Or
Yes. So the muon left or right both have say quantum number 1. Then tau left and right has -1. Both left and have included.
Okay, so with respect to the Z2, the leptons are vector-like.
Right.
So the coupling to the Z2, is this chiral or is this vector-like?
Well, you start with a chiral, then it turns out the muon and the tau, because they have left and right particles, so then the coupling becomes vector-like. So you don't, and that's why you don't have anomalies. But then for neutrinos, you only have a left-handed neutrino. The right-handed, if you don't introduce a right-handed, then this will be chiral. So this will, the anomaly for this guy will cancel because of this minus sign here. That's all. Okay. So before the Brookhaven finally sort of round up the data in 2001, so g-2 have not become a central issue, but then since then become more and more sort of prominent. People say, "Oh, okay, this 2.7 sigma, we need to find some solutions." So at that time, Pyongyang and also Swan-Bay coming from here, and the Shipenda from Oregon, we took up this model to say, "Oh, okay, because this muon interaction here, this Z prime, naturally you don't modify g-2 of a muon, right?" As I said, tau is more sort of not so accurately determined. So but then you can also go say muon minus electron. But then electron has a very precise, so well, that's why people don't talk about electron. So then you do that calculation, then you will find the g-2 divided 2 is given by this formula. Okay, so this formula, if Z prime is much larger than muon mass, then you have a very simple expression. It's like this. Okay, but then if muon is this Z prime mass is similar to muon or even smaller, then you have to work a little bit harder. If in fact I work out some integration. This is integrable, but that looks very funny and complicated. So then Pyongyang said, well, maybe we keep this formula looks simpler. Now this is the formula in the literature. Only keep to this formula. If it just you can solve the integrate out, but then it doesn't help much. Of course, now these days very easy to do numerical calculation. I threw in the numbers of what is the prime mass you want. I just give the outcome. Okay, so now if it's much larger than muon, then this is simple. So in this talk, when I say small or large mass, this is the Z prime mass compared with the muon mass. So it's much larger, then we say Z prime is large. Then it's a similar or lower, then we say, well, this is Z prime small mass. So that's the small and large I was referring to in the title. Okay, so then you want to produce this 4.2 sigma, let's say, take the central value, and then you will, because this here, this determinant, this determinant is the ratio of G prime, G cubed square divided by Z prime mass squared, which is not determinant. So, but then the ratio from G minus to you will determine to be this way. Okay. So, if the story stops here, then I don't need to give talk here. This is too trivial. Well, first you notice, in fact, this strength is similar to Fermi constant, right? Fermi constant is 1.16 times 10 to the minus 5 divided by GeV squared. So this is kind of large. Then you maybe they say, well, really we can accommodate such a large number, or you have to maybe tune your parameters to see what maybe you can avoid the constraints from others. But then in the beginning of the century, data not too many, so this can easily sort of slip to all these scrutinies. Say that okay, but then now you have more and more constraints. Okay, so then I will talk about this constraint. One of the strangest constraint I think so far is this trident neutrino experiment. So if you look at this Taiwan, look at like some sort of trident, right? 3 things stick out, right? So what is this? This is a muon neutrino hitting a nuclear target. Then you produce a muon and another muon neutrino come out, and another mu will come out. So this is a Taiwan in the standard model. One of the Taiwan can do the job. Now, for this here, you can also exchange a Z, but then Z is much the energy exchanged here is not bigger. So Z exchange is very small, so you can neglect it. So basically this one. But then you can also have a Z exchanger here to do the job, right? So then you can do the standard model calculation. But then if you have an additional Z prime interaction with a neutrino and the muon, like our model, right? So our model gives you muon and the muon neutrino. So then you have to go coordinate to do the calculation. And then you will find, okay, so this is the vector-like interaction of Z interaction with the, and then this W you can make, because it's heavy, so you can make a field location. Then looks like effectively, if you shrink this to a point, is a mu come out, so it's equivalent. So then this W will contribute to here too. But then this Z prime for muon interaction is a vector, so it will come into here. Now this is a 1 because this Z particle has this and also this one here has a gamma 5. So this one is what cannot see, but it is a 1. So you have these contributions. Okay. So now you see these are well known 0.3, 0.23 something you put in, and then this one here we know W mass, we know G, then we know if you want to solve for G minus 2, this thing needs to be somewhere here. Okay, so then you say, well, I put in here, then we'll find the modified trident cross section compared with the standard model prediction. Well, if you use this formula, you will get 5.86. Well, so in the standard model is equal to 1. Now you, because of this is become almost 6, then you expect something like 1 to 1. But then if there's no data of measurement, then you can say, well, okay, maybe this is a chance for looking for new physics. But then now we do have some data, then you better not to upset the data too much. Okay, so what is the experimental data situation? You have 3 measurement similar type. You get this one, this one, this one. Okay, so it doesn't matter which one you believe. It's much smaller than 6 central value. And also, if you average it, then it's a 0.95, something plus or minus 1.3 something. So this thing is to say, well, the trident experiment will definitely rule out this scenario when Z prime mass is much larger than Muon mass, and then and also this number to be here. So that means you cannot do the job, okay, by this model, simply like what we did a long time ago. But then it's okay. We did it 20 years ago, 22 years ago, and the people still citing our papers because this is the idea is still working. But then now, in order to do this, to get this satisfied, what can you do? Now, here I use this number because I say, well, the Z prime mass is much larger than Muon, and then of course in this formula, the exchange Q square is of order Muon, because if this is not too large from pi and decay, all those sort of things, then these will be the Muon mass, the so-called exchange the energy. So that means if I have this Z prime, which is small enough such that this here, they have sort of similar type of thing, then your calculation, the simple approximation I made before, will not work. So it will not work. So I have to keep it a lower mass. At the same time, you do trident cross section the similar way. So this is this turned out to be not trivial because at the low energy, as I said, you have 2 propagators of order the same, then make it the calculation easy. But then numerically, people has done as well. So now, this green range, this is excluded. What is the green range is excluded by trident experiment. So anything inside of here is not allowed. Okay, but then if you do G minus 2 with a large mass and a smaller mass, you find, well, this strip, this band is you want to solve G minus 2. Okay, so then you find say, oh, okay, maybe if my mass is less than somewhere here, maybe 0.3 or 0.2, and then this range is still allowed. Okay, so from this here, what the conclusion you can draw is, well, if you still like one gauge theory of Muon minus tau on that number, and then this is a surviving range. So you should be looking for some Z prime is much smaller than the Z mass or W mass, so similar order as Muon mass. But then the coupling will become 10 to the minus a few times to 10 to the minus 4 or so. So this is also non-trivial experiment, so you need very precise measurement. But then basically the ratio should be some number, still kind of for Fermi constant sort of level or some number. So it's not impossible, but it's difficult. So then the question now, people will say, well, okay, so is this D prime must stay such low? The larger mass is not allowed. Okay, so now address these questions. Okay, so the answer, if you modify your model a little bit, then it's possible to still have Z prime mass to be large. Okay, of order 100 GeV also, for example. So also long time ago, people find if you have some discrete symmetry of a Z2, so you change Z prime to minus Z, mu to minus tau, tau to minus mu, and then you find your coupling of Muon, Taiwan, and Z is going to be like this way. Okay, mu, tau, tau, mu, neutrino, Muon, and tau. Okay, so now if the coupling comes this way, the trident experiment is naturally forbidden, because the trident need to neutrino come in, produce a muon neutrino, produce two muons. So then the tree loop diagram just a tree diagram is just shown. Then this will not do the job. Now you say, oh, okay, so simple. That just get rid of it. That's all. But then because of this interaction, then we'll find that tau can decay into a muon through mediation of Z prime into two neutrinos. Then this is allowed. Okay, so experimental data says, well, this should be less, it should be almost like a standard model. So 1.06. And then you say, well, okay, I want to solve for g-2, because this time I can have this in the loop. In fact, is an enhancement, so I need this to be smaller. But then you do that, you find that this one, you put it into the 3 decay, so you find it's 5 sigma away from the data. So that is, you cannot do it. So this is something coming. Then you must find something which you can lower this type of decay. Okay, so what you not only forbidden the trident experiment, you can also somehow make this one to be small. Okay, so how do you do that? Then, in fact, before I also say this Z2 symmetry, you get the coupling like previously given. To do that, you need to introduce 2 Higgs doublet. Yeah, that's a 3 Higgs doublet. This one to give the first generation electron mass. This to the mu and the tau masses. But then you have this symmetry, and then you say, well, the valve does not break this discrete symmetry. Then you will have the coupling given before. But then you say, well, that has a problem with tau to mu and 2 neutrinos. Then you want something else coming to cancel that calculation, contribution. Then you notice this type 2 seesaw can couple to next page. This here. Without this one, then you will get this. That's what you will get from what I just showed. But then, as I said, this one is problematic. Then you need to introduce the triplet doublet, the triplet Higgs. Yongjin is expressed on type 2 seesaw. It's not. But then I will not use it primarily for neutrino masses, but I will use it here to solve my problem. So this guy can have that, right? So that's why the type 2 seesaw can give small neutrino masses. The values are very small. But then now I will want to keep my Z2 symmetry. So I introduce 3 delta triplet Higgs. Again, the symmetry is similar to the Higgs 1, 2, 3 H. And then you will find this guy coupling to leptons. You have 0 components. neutrino mass, and then its interaction is like this. You have a doubly charged Higgs, probably with a charged electron this way. You can also have a singly charged particle go like this. And now you notice, well, this guy, if I exchange a delta between this guy and another guy, then you will be able to generate a. If this is a mu, this is a tau, this is a electron neutrino, muon neutrino, tau neutrino. I will have this mu, tau to mu neutrino type of interaction. Okay, and then you do that, you find this scalar contribution with this charge conjugate modes. Then you find the contribution has different sign, like compared with z prime. So then that gives a chance. Well, this, if you introduce this, it will cancel the z prime contribution, and then I will be surviving from this tau to mu sort of interaction. Okay, so then you work at the details, and then you say how it interact with muon and the tau and the electron. Then this is the new interaction. So by exchanging triplets, Higgs, then you will generate this rho mu, rho tau mu, rho mu tau. Rho mu and the tau is given by this delta 2 plus or minus this 2. Then you have delta 3. You have these two contributions. And also this mu tau mu appear here is given by this delta 1. Okay, so now you collect all this information and say to what I'm concerned. We are concerned about tau to mu then it's tau to mu that looks like this. So before we have this standard model contribution, then we have the z prime contribution. Now we have this additional contribution. Then tau mu is this one here. Oh, sorry, tau mu is this one here. So now, because of this is without this thing, this is dangerous, right? So that's make too large tau to mu contribution. But then now, hey, this side has different sign. Then what happens is okay, I choose some masses and the couplings, and then I get this to be cancelled. So that means this one cancel this one, then whatever left is the standard model. So now I'll be able to get equal to 1. So there's 5 sigma things I can get rid of. But then, because this is the new interaction, you can also introduce tau to mu. You have a gamma 5 here, then you will have this contribution, right? But then this contribution, you also can make some modifications such that this is not ruin my sort of result. So this is okay. But then you have all these guys. These guys are also you can adjust the contribution. Okay. But then at this time you will find this one here. But then I still don't have this trident thing. But then this will have tau to mu, 2 muon neutrinos. But then you can control mu to get it small enough. Okay, so you collect all this information. It seems whenever you have something, also this delta will come to help to cancel the sense for you. And then you exchange to delta, you will introduce tau to 3 mu also. This has constraints. We didn't use mu to 3e. That's very much stronger. But then we don't need it because our concern is g-2. We just do this. Then this one here. But then if you choose these two masses to be close to each other, then this can be easily sort of lowered down to the experimental bound. And then you have a g-2, and from the Higgs contribution, all of this. See, even if this is cancelled, then it becomes a plus. Then you might have something, but then this is it turns out you can control it to be smaller than upper bound. Then you leave the z prime maybe to do the job. Okay. Also, trident coming. So before there was some big contribution, it's a positive from z prime, but then we don't have this trident contribution from z prime, right? But the Higgs will have some contribution, have some contribution. It's giving back this here. Again, you can control the numbers so that it's small. Okay, so now having all of this, we can collect all the data, and also this how to mu gamma also comes to some constraint. And then once you get this rid off, this is the same time get rid of them. And then to subject this one here, you make this almost zero. So now, because of the still the more parameters, the constraints, then you can choose some numbers. For example, we choose this one to 0, and then see what others come to play. So now the trident data exclude anything above. The g-2, you need to be in this range to explain it. And then this tau to mu is allowed in this range. So then we still have a parameter space such that everyone is happy. Everyone is happy. So that means in this case, my z prime, we don't need to be very small, less than 300 MeV. So any number is allowed as long as you are in this range, the coupling is here. Okay, yes.
One question. You introduced new Higgs fields now.
Yes.
Are there any constraints on those Higgs fields or on the couplings of those Higgs fields to the core?
Yes. So I was these Higgs do not come to Higgs because it's a triplet. Triplet it doesn't only come to left-handed L Chinese conjugation. So I'm safer with quarks. Yeah. Here is sort of from the very beginning. I'm trying to not to touch quarks. All I'm saying is that
There's no bound from HC search for doubly charged Higgs.
yes.
So
Yeah.
that's
This
about 800 GB.
yes. That is safer because see this Y22 depends on what your Higgs what your value is, right? That can be
No, it does depend. I mean, probably you need the large Y22, right?
yeah.
And then this double charge should decay mu dominantly or tau.
Yes, we will have checked that about this.
There could be also another bound from lepton universality of G decay.
Also taking care of it. Yeah, because in a previous paper, we were studying all of this and say, well, you have to satisfy this, and then everything will change. It's okay.
So that bound should compare to tau mu nu, right?
Yeah.
Okay.
Yeah. Okay. So the conclusion is okay. So I can have a larger Z prime mass or small mass, depends on what you want. But then, of course, the different unit is well, okay, you have all this constraints. Maybe you have some new signatures. So this seems to be particular to this type of model. Okay, so E plus E minus, you can produce Z, you can do this. Then you always have alternating in charges, right? Alternating charges. But then you have this particular Z prime to solve this, then you will have different coupling. For example, so this type of thing, you can gamma Z, then you can put mu, but then you have a Z prime coming here, then Z prime will change it mu to tau. This here, you can have a mu tau here. Then you can have mu minus plus mu plus tau minus sort of a signature. Okay, so that's a very different from a Stein model, or the other way, minus plus. So this will be the signature of this new type of thing. Now we are doing some calculation and to see how this can be sort of produced at, for example, now E plus E minus machine as a CPC or FEE, and proton. Actually, you can try this LHC also. So this is in progress.
Sorry, are you assuming Lepton flow violation here?
Left down.
So initially you talked about Lµ minus Lτ, which.
Yes. Now I have to shift to the paradigm.
Okay.
Yeah. So there you find it difficult to have a larger. Then I wanted a larger. Then what can do? But then this is simple enough. Yeah.
Okay.
Yeah. You change the Z prime to mu and tau.
Okay.
But then this is sort of extremely extreme. You don't have a mu, you don't have a tau, but then just mu tau. Okay, so then this will be the new signature of this particular type of model. So we are doing the calculation of some experiments, so maybe getting interested and use the data to constrain. Maybe it's ruled out, or maybe, well, they don't have one much. I don't think it currently they can rule out, but then in the future. So let's talk about conclusion. The simplest of the Muon mu minus Lτ. Then you will find the Trident experiment constraint the g-2 solution very much. So it should be less than 300 MeV or so. So then low energy, maybe taper type of experiment, maybe looking some very precise measurement, you might find some hints. But then if you say, well, I really want my LHC to still have a job to do, right? They don't find Higgs, they don't find such, and then something else maybe. Then the Z prime, larger Z prime is one of the possibility. Then some new signature of this type, maybe worth noting. So good luck if anyone wants to look in for. So this is the smoking gun for this type of model. I'll finish it here. Thank you.
Thank you very much for the nice talk. Any question?
How do you consider the kinetic mixing?
Kinetic mixing. For this particular model, it doesn't happen. Why? The original model will have a kinetic mixing, but then this here, because of this Z goes to minus Z, and then the hypercharge, let's call it a Y, I feel that does not change it. So there's a kinetic mixing, Z mu, Y nu will not happen because that is all under this Z2 symmetry. So that's forbidden. Now, then a lot of questions then is related okay, so the ordinary one, you don't have this mixing. So then this here is possible to have this kinetic mixing. But then that one, we have checked, see if the kinetic effect is large enough to alter the conclusion. No, because the kinetic mixing is constrained. Say if we put the epsilon, then epsilon is constrained to be less than 1, and then if you make it too large, then you will upset other others. So you cannot go to opposite of the others, then will not help the situation here. Yeah.
What's the maximum mass that Z prime can have to solve the G minus 2? Because as you make it heavier,
Yes.
the G gets heavier.
Yeah.
Larger.
So basically, then it's controlled by this equation. It's more or less controlled by this equation. When you go large, this behavior is like that. So how large you want to be? You want the ratio to be around here. So if it is too large, then you need this to be too big. So maybe you make a unitarity constraint or perturbativity constraint is to be less than 1 or pi, 4 pi, and then that's the number you can get. So I think it's 1 TeV or so.
300 GB. 300 GB. 300 GB.
300 GB.
Should be found soon.
Yes. That's why some people say, well, okay, so there's a small. Yeah.
It also cannot be very light, right? Because otherwise it will decay to like neutrinos at very late time. I mean, it's fine. Cannot be very light also, right? Like MeV or something.
Well, I think for light one, there's not much problem. Oh, sorry, wrong direction. So you say, well, the mass is too low, something. So this Z prime is light. You don't have much data. So even though it decays to neutrino, or what?
Yeah, I mean, if it decays to neutrino after neutrino decoupling, so that's not allowed, right? I mean,
In fact, there are a lot of beam dump experiments excluding light masses.
Yes. But in this parameter space,
Yeah, it's okay.
Yeah,
But
it's
below, I mean, it's basically excluded by.
no.
I mean,
wait a second. Listen, see, when this light mass comes to zero, there's no data. In fact, but then in somewhere maybe EV range has some constraint. So, but then the coupling is -3. So it's its square is -6. I'm not aware.
I'm not sure whether this was your question, but are there any cosmological implications if the Z prime is very light because this is inducing
Yes.
neutrino salvage?
Yes, I think that these are related. So then you all get into the BBN effect, all this stuff. That one, I think we don't need to go in that region, but then you put, you have to in a region. There should be some constraint. But then for addressing this G-2, you don't need to go to that region.
I want to ask for LHC. If I see correctly, the signal you get there is same sign leptons with additional taus.
Yeah.
For which, at least in the production, LHC should have more prospects to produce it than plus and minus machine.
The what machine?
So
The proton machine.
whether this is better at a plus and minus collider or at a proton-proton collider, but this is basically kind of Drell-Young production.
Yeah.
2 leptons,
Uh-huh.
and you get suppressed because of the Z prime radiation. But this signal, even at LHC, almost was close to being background free.
Yes.
Same sign leptons.
Yeah, but then the people has not carefully studied this. That's why we are doing the calculation.
One clarification. So in your modified model, you have extra charged particles.
Yes.
And maybe some of them can contribute to Muon G-2.
Yes.
So they are all irrelevant? Or
Yeah, so we have the included here. So G-2. Then you have this charge, doubly charged and charged. This
they
given
give
here,
a negative contribution?
the negligible. So this is a square or
It's, there must be actually. So basically, the lower mass explaining Muon G minus 2 in Lµ minus Lτ model excluded by Orexino and White-Tau. I mean, below 10 to minus 2 G.
Oh.
Approximately. So this is G minus 2 band.
Yeah.
Then this 10 to minus 2 times 10 to minus 2. Lower mass. is excluded.
Okay, that's good. That supported me to get rid of.
Yeah, so that's why you cut.
Yeah, that's even more constraint. Yeah. Okay, so I would look at them more carefully for that.
Any other question?
In the usual type of two seesaw model with one triplet, the custodial symmetry constraint, the triplet web, it should be very small. So how in this model?
Yeah. So for this year, there is a small, say, from raw parameter is about a few GeV. But then if you say, well, I wanted it to be produced the neutrino mass, and then I can below that anywhere is okay. That well, if you smaller, then you will get the Y, the coupling and bigger and bigger. Okay. So, but for this purpose, I said there's a large range. This valve for that scale doesn't do much because see this here I don't have anywhere this valve itself coming to somewhere, so it doesn't affect much.
Other question? If not, let's thanks speaker again. Thank you very much for the nice talk.
Okay, so thank you very much.